In this lecture, lecture 8, we are going to talk about two items here. The first item is transmission line trace on the Smith chart, and the second item is how does the Smith chart work. So let's get started. The first part is about transmission line trace on the Smith chart. So in this regard, we're going to assume this network here, a source connected to a transmission line with a load at the end. So this is our z coordinate as we have labeled it in the past. Z is equal to 0 right at the beginning of the line, z is equal to L at the end of the line, and also we had another coordinate system here which was going backwards for convenience of writing certain equations. The d coordinate starts at the load side, d is equal to 0, and would be equal to L at the source end. I'm going to assume a couple of locations on the line, Z1 and Z2. At each of these locations, I'm going to label the complex reflection coefficient gamma 1 and gamma 2, and the driving point impedance at this location here would be Z1 and Z2. Always use the driving point impedance expression assuming that we are looking from the source towards the load side kind of thing. If the problem requires that you work backwards and look at the reflection coefficient backwards or the impedance backwards, we would be looking at the this side to be the load and this side to be the source, and the labels will be all opposite. But in general, we will be always labeling things in that direction. As we have discussed earlier, the gamma and the impedance, both the reflection coefficient and the impedance, are functions of position. And we can always write the gamma in terms of z at any given location, as well as the gamma at some location in terms of gamma at some other location, the impedance at some location in terms of impedance at some other location. All these equations were developed earlier. So recalling some of these equations, gamma of z, for example, is equal to gamma of 0 e to the 2 gamma z. All right. We can rewrite that in terms of alpha and beta, so we can write also the distance moved kind of expression. All right, so here's the one that expresses the distance moved. Gamma of z is equal to gamma 0 e to the 2 alpha z e to the plus j4 pi z over lambda. All right, so this is the distance moved. Similarly, I can write gamma of z in terms of gamma of L at the load side. Again, I can write it again in the form of e to the minus 2 alpha L minus z, and again the distance moved normalized to the wavelength. We can rewrite those expressions in terms of d because L minus z is actually d, and that's the reason for using the d coordinate system is to substitute L minus z by d. So this is the same exact expression right here written in terms of the coordinate system d. These equations here are going to be useful to us in the discussion of the trace. Magnitude wise, we discussed it earlier. The magnitude will depend on the alpha. If there's loss on the line, the magnitude is going to change. If there is no loss, the magnitude is going to be constant. All right. If alpha is 0, your gamma of z is going to be equal to gamma of 0 is going to be equal to gamma of L is going to be gamma everywhere. All right. While the angle changes by a certain amount, and that amount is determined by the distance moved normalized to the wavelength. So these are the two expressions here that we will be working with. One again with the z and one with the d, and again the reason for the z or the d is whether you are moving towards the load. In this case here, you rather use a z. If you are moving towards the generator, you might rather move the d. Okay, here it is, moving towards the load, we would be using the z. If we're moving towards the generator, we'll be using the d. So let's start with the lossless situation. Case of alpha is equal to 0. In other words, the line is lossless. In this case here, this term here is 1, and therefore gamma of z is equal to gamma of 0. and gamma of D is equal to gamma of 0 or gamma of L. They are all equal in magnitude, whichever way you move, whether you move towards the generator or move towards the load. Again, your gamma is a constant magnitude phasor. So the trace is obviously going to be a circle. However, the phase is going to change differently. Let's look at the phase part. The phase in this case here, all right, let's look at the motion towards the load, and you can see that the phase is going to increase by 4 pi z over lambda. So moving towards the load, all right, here it is. The phase is increasing. That's the direction of the angle increase. So if you start here with gamma n right there, and you move towards the load, your gamma angle is going to increase. So that's your gamma n, that's your gamma 1 right here. You move to gamma 2, angle is going to increase more. All right, gamma L will be right there. So moving that way, your angle increases. And the increase is going to be determined by the ratio 4 pi z over lambda. And that's the scale that we have here. Remember that scale? We had a scale here that goes and calibrated in terms of z over lambda. So 4 pi z over lambda determines the first change in angle. If you go to the z2, that's 4 pi z2 over lambda. If you go all the way to the load, that will be 4 pi L over lambda. All right, the angle here is 4 pi L over lambda. If you read it on the angle scale, if you read it on the L over lambda scale, obviously the 4 pi is already embedded in the scale, so you just put down L over lambda and you move from here to there. If you are moving the opposite way, right, you start at the load, so here it is, D is equal to 0 here, and you're going to move this way, so we're going to move that direction, and if the first motion will be towards Z2, so that's your D2 over lambda, here's D2 over lambda. You read that on the scale. D1 over lambda, L over lambda. It's the same exact angle, but obviously motion this way versus motion that way. Okay, so that is how the trace looks like if you have a lossless case. All right. Let's move to a lossy case. All right. So we'll jump to this slide, and here we have a situation where the gamma magnitude is not the same anymore, because the gamma magnitude is going to change by e to the 2 alpha z. Now, if I'm moving towards the load, my z is increasing and e to the 2 alpha z is increasing, rising exponential, and my gamma of z is going to increase. So if you are moving towards the load, here it is, and I start at some location, where is gamma n? Right there is gamma n. Okay, then I'm going to be moving on a spiral that is going to spiral out, increase. Right, starting with gamma n again. That's the length. The length here is bigger, the length here is bigger, the length here is bigger and bigger. So e to the 2 alpha z is going to increase, and I'm going to be spiraling out. Okay, and here it is. Moving towards the load, you spiral out. Depending on the alpha, if alpha is very small, that's going to be almost close to a circle. But if alpha is big, the change is going to be bigger, and the spiral out is going to be more pronounced. Let's go to the opposite direction. If we are moving towards the source, look at this equation. Now D is increasing. Moving towards the source, D is increasing. So you start with 0 and goes on and on and on until it reaches L. So the expression here has a minus sign because the D is opposite to Z. And therefore, as D increases, e to the minus 2 alpha D is going to be reducing, and the gamma of D is going to be shrinking, and your spiral in. So if I start at the load here, okay, I start at the load and move towards the source. I start at the load. Here's my gamma of D. Gamma of D is equal to 0. Here's my initial gamma, and I move towards the generator or towards the source. I'm going to decrease my gamma gradually, and you're going to see a spiraling in. In fact, it's the same exact spiral. It's just where you start and where you end. It's the same identical spiral. So if you are moving towards the load, you are tracing the spiral in this direction. If you are moving towards the generator, you are moving on the spiral in this direction. Now, those spirals are not on the Smith chart. You have to lay them in depending on your alpha. There's alpha could be any value, could be 0, so you have circles. You draw your own circle. Could be small, could be large, so you draw your own spiral on your Smith chart, and basically this is the equation for your spiral right there. This one or that one, it's the same exact equation, it's the same exact spiral. The second item in this video, which is in lecture 8, is how does the Smith chart work? And in the lecture material, we have a very simple example here that you can read on your own. And instead of going through this example, I'm going to go to a different, bit more elaborate example. All right. So this is the example that we are going to work the Smith chart with and demonstrate what can the Smith chart do for us. In this example here, it's a transmission line network. It has a load. At some location here on the line, I have a shunt impedance, or a ZP. At some other location on the line, I have a series impedance, or ZS. And the interest is to find out what would be the input impedance of this whole combination and what would be the reflection coefficient at the input side of the line. I'm not showing the source here because it doesn't really add much to our purpose here. Our purpose is to find the reflection coefficient and the input impedance. So here we start, and going to show the transmission line on top of the Smith chart, and I'm going to start at location 1 here. That's location 1 where the load is. So I take the impedance of the load, normalize that, and put it as a real part and imaginary part, and locate it on the line. I locate an R circle and X circle, and the intercept would be my point, and this would be my gamma phasor at this location. So that's actually your gamma L at this location here, where point 1 represents the impedance Z sub L at that particular location. Next, I would move on the transmission line. I'm going to assume it's lossless, so I move on a constant gamma circle, and I'm moving towards the generator, so I'm rotating to the right from point 1 to point 2, and the distance moved will be the distance from the location 1 here to the location 2 there corresponds to L1 over lambda. Alright, next I recognize that I'm going to add a shunt impedance, so I need to work with admittances because admittances add in shunts. So instead of Z1, I'm looking for Y1. So point 2 here, which was the impedance at location 2, corresponds to point 3 here as an admittance. So point 3 here is the admittance at that location. I need to add it to the admittance of Z sub P. So that's going to be my next move. Add this admittance to that admittance to get the admittance at this location here, which is correspond to Z2. All right. So how we're going to do that? So we look at normalized Z sub P and get the admittance of that. So I take Z sub P and convert it to Y sub P and break it into a real part, G sub P, and imaginary part, which is B sub P. And that's exactly what I'm going to do now. All right, I move here by adding the real part to the real part. So I move from this point, which is point 3, which was the admittance of the line at this location, and add the real part G sub B. And in that means I'm maintaining the same imaginary line. So on the same imaginary line here, I'm moving a G sub B. So I'm moving here partially towards the final point, which is going to be 0.5. And then next I add the B sub P, and that would be a motion on a constant real part circle, and whatever that value is, I get there, and that would be my total admittance at 0.5. So 0.5 is represented here as an admittance. You have to keep track of that, whether it's impedance or admittance. Again, remember, this was the impedance at the load, the impedance at 0.2, the admittance at 0.2, and adding the G and the B of the parallel or the shunt impedance, G sub B, bring me the admittance at 0.5. So I have the admittance of 0.5. Next, I'm going to go to the other transmission line TL2 and add a series impedance. So eventually I have to convert the admittance here to impedance anyway. 0.5 is at the beginning of this transmission line, which is again going to be assumed lossless. That means the trace is going to be another circle of radius that much. This would be the magnitude of your reflection coefficient at 0.5. So if you want to get gamma 2, which is at 0.5, this is this magnitude. But since the Smith chart represents the impedance on the reflection coefficient, the admittance actually is represented on the negative of the reflection coefficient. So this is actually the negative of the reflection coefficient at 0.5. To get the positive one, you have to go to the opposite point right here. So that's exactly what we're going to do. 0.6 is the same as 0.5, except 0.5 is actually a representation of the admittance, 0.6 is a representation of the impedance, and therefore gamma 2 is this phasor here. This would be negative gamma 2. This is positive gamma 2. So 0.6 represents the phasor gamma 2 at location 5 or 6. Now, I need to move L2 over lambda, and again that motion is towards the generator, so I move in this direction here, and that's going to be the next one. There we go. So I move to 0.7, which is a distance L2 over lambda from 0.6. So that's the impedance of 0.7. Now I need to add the series impedance Z sub S. I'm going to add that again in 2 steps. I'm going to break Z sub S normalized to real and imaginary parts. So I'm going to add the R sub S and the X sub S, one step at a time. Here we add the R sub S. No, I'm adding the X sub S first. All right, matter. Whichever way you do, you're going to end up with the same final point. So I add an X sub S. That means I move in on a constant R circle. That's a constant R circle right there. Okay. This one here is a constant R circle. So I added on the circle here X sub S. That means the value of X here and the value of X there differ by the value of X sub S. So I got my 0.8 here, which is a partial motion in here. Now I need to add the R sub S. And here we added the R sub S, which is a constant X circle now. This is a constant X circle. And the value between this R circle and this R circle here is the R sub S that we added as a result of this series thing. So finally 0.9 here represent the impedance at 0.9 there, because I added the impedance here to the impedance there, so I end up with the impedance there. So 0.9 here represent the input impedance at that location. So all I need to do now is connect the line between 0.9 and the origin, and I have gamma input. Okay, here it goes. So this is gamma input, and this point here represents the impedance at this location here, and that would be the final answer to gamma n and Zn. So again, to demonstrate the whole thing, let's go over it very quickly. I start with the impedance at 0.1, constant gamma circle, lossless line. I move to 0.2, impedance, get the admittance, 0.3, add the shunt admittance of the shunt device here connected, get the G sub B and the B sub B, which is the inverse of that, normalized admittance, move the G sub B and the B sub B, I get the admittance at 0.5. Now I want to get the impedance, so I go opposite 180 degrees, I get the impedance of 0.5 or 5 or 6, the same name, 5 or 6, that's the impedance right there, which is means that this is your gamma at that location. Gamma 2 is right here. And then I move the distance L over lambda, L2 over lambda to 0.7. Here's 0.7. Then add the series impedance Z sub S. I added the X first and then added the R later. Finally, I find the total impedance here, the driving point impedance, the input impedance at 0.9, and that would be the gamma input at that location. I hope this example here demonstrates solving a problem like this, which could have been a bit more elaborate if you do it analytically. I'm going to show you how to carry on that in an analytical fashion in a minute. To solve this problem analytically, let's see what kind of equations we need. We need two equations here. We need the gamma related to Z, and we need the gamma related to gamma. All right. These two equations are already in your notes. All right. Let's look at the first equation here. This one here basically tells you that gamma at n location, and we're using the coordinate D because we are moving from the load to the generator. So the coordinate D is most suitable here. All right. Gamma of D is the ratio between Z of D minus Z naught divided by Z of D plus Z naught. So that's gamma at n location on the line here. Okay. So at the load end, we can start with that. We can start knowing ZL right there. Z naught is already known. I can get gamma at that particular location. So I can just put D as subscript L here. So gamma L is equal to ZL minus Z naught divided by ZL plus Z naught. So I can find gamma L knowing ZL. Right? So I use this equation right here to find gamma at L. Now I know gamma at L, I need to get gamma at 1. So I use the second equation. L, the location L is number 1. The location 1 is actually number 2. All right? Just a matter of notation. Okay. So to get gamma in this location here, which is gamma at D2, which is gamma 1, is equal to gamma L e to the minus gamma minus 2 gamma, the difference between D's. I already know the difference between the two D's. D is equal to 0 here, and D is equal to L1 right there. So actually, D2 minus D1 would be that D minus that D, which is L1. So I use that. Knowing gamma at the load, I can get gamma at the first location. So I can get gamma here. Knowing gamma here now, I can get the impedance here. I go back to this equation here. Knowing this gamma, I solve for the impedance. I get the impedance here. I add it in parallel with that impedance. I find the total impedance here. I know the total impedance here. I can put it back in here and get gamma there. You can get gamma there. Knowing gamma here now, I can get gamma here using this equation. So starting with gamma here, I can get gamma there using this equation. Knowing gamma at this location, I can find the impedance at this location using this equation. So I'm going back and forth. All right. Now you found the impedance here. You can add it in series with the impedance there. You find the total impedance at the input. Knowing the impedance here, I can get gamma there again using this equation. So as you can see, you are going back and forth in these two equations. This equation is the Smith chart. This equation is the trace moving on the Smith chart, whether it's in circles or spirals. So as you can see, I'm combining the Smith chart with the added graphs that I do on the Smith chart, whether it's circles or spirals, to get the total process. So as you can see, went back and forth, and that's exactly what we did when we solved that problem on the Smith chart. As you saw, the graphical solution was much nicer and was kind of visual. You can see what you're doing. Here you will have lots of complex manipulation. You can program this into a computer and get the final answer, but you wouldn't have the same visual insight in the problem as you would have doing it with the Smith chart.